Okay, here is our final activity in looking at amplifiers and amplifying microphone inputs and audio inputs. Let's just clarify what we mean by audio inputs. If we look at this little block diagram here, what we can see is that we have signals coming from radios, CD players, DVD players, MP3 players or microphones, and we might want to listen to them on loudspeakers, headphones, or even send them to a recording device. And the problem is that these signals are so small that actually these systems wouldn't be able to do anything with them. So we need to amplify that signal to make it a little bit bigger. Now we've looked at using the 741, which is a fairly standard operational amplifier, but we're going to look at now an audio amplifier designed specifically for this purpose. And it features in the AQA GCSE examination. So here is the inside of it, and it looks pretty similar to our 741. The difference being now that actually that we have the power pins just slightly different. I'm just going to move that up a little bit. Our V out goes to a different pin, etc. But generally it is an operational amplifier with inverting and non-inverting inputs, but we have these two pins here, pins 1 and 8, where we can change the gain externally. It can be run off a battery. It doesn't require calculations on gain, and I'll show you some circuit diagrams in a short while. It can run off a range of voltages between about 5 and 18 volts. And the gain that we can alter within it is from 20 to 200. So let's look at the circuit diagram. And there we go. This is the one that I'm going to build, and I'll show you a couple more as I've said later. So we have the microphone coming in, but I'm going to be using an audio signal from the frequency generator initially. Our loudspeaker output, we've got these decoupling capacitors here, or a decoupling capacitor on the output, so stopping the AC and the DC from interfering with one another. And this is our gain pins, pins 1 and pin 8, where we've got a 10 microfarad capacitor. So let's look at that. So here is my circuit, and what I'm going to do initially, I'm going to put in a waveform of a very small magnitude. At the moment we are sitting on two divisions. This is our input on channel 1, and each of those divisions is worth 20 millivolts. I'm just going to write that down. So our input is 2 divisions times 20 millivolts, which is equal to 40 millivolts, which is equal to, moving our decimal point back 3 for the millivolts, 0.04 of a volt. So that's quite small. Let's look at our output. So I'm going to move to channel 2. So I'm looking at the output pin, and the output shows it as 1, 2, 3, 4. 4 divisions, but now each division is worth 2 volts per division. So our output is 4 divisions. Each division is worth 2 volts, which means that the output is an 8 volt output. So what is our gain in this circuit? Well, our gain is equal to out over in. So our out was 8 volts and our in was 0.04 volts. Using our calculator, out 8 volts divided by 0.04 volts going in equals a gain of 200. Now I'm glad that's 200, and I'll explain why in a short while. So our gain here is 200. Let's look at the two together. You will also notice that it is a non-inverting amplifier the way that we have configured it and the way that it is used. So how can we tell that there is a gain going on? Well, first of all, what we can do, we can listen to the input. So my input is coming from here. So I'm going to listen to the input on the loudspeaker. Hopefully you can hear that. It's quite faint, so that's 0.04 of a volt across that loudspeaker. Now what I'm going to do, I'm going to plug the loudspeaker back into the circuit. And we've got a bit of noise going on there. And now I'm going to plug that to the input. And immediately you can hear that is substantially louder once it goes through the amplifier. So our input goes in through the amplifier out to the loudspeaker. That is with a gain of 200. And one of the important things about this circuit is that the LM386 is also increasing the current to the loudspeaker because it's considered a power amplifier, although not a terribly big one. I want to have a quick look once again. I'm going to unplug the loudspeaker before I plug in the microphone, and I'm going to just have a quick look at what happens when I increase the input. So as I increase the input, watch what happens. So our input, just to qualify, is that one there, the one wobbling, the smaller one at the moment. So even though of course it's considerably smaller, watch what happens as I increase the input. I'm going to just turn there. I'm just going to look at the output now. I'm increasing the input and the output there is saturating. What is it saturating on? Well, it's approximately 1, 2, 3, 4, 5 and a bit divisions, and each division is worth 2, so it's just over 10-11 volts. Well, of course, if we go back to our circuit diagram, you'll notice that I used a 12-volt power supply in this one, so that's about right. Okay, let's go back. I'm going to remove my sine wave going in. I'm going to plug my loudspeaker back in, and now I'm going to plug my microphone in. Okay, let me cover up the microphone. Okay, I'll explain what that noise is in just a second. Now I'm going to talk into the microphone and hopefully we should hear something. Hello, hello, hello. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm talking very closely to the microphone here, but we can hear the output on the loudspeaker. Okay, so the microphone was definitely amplified, albeit not a terribly good quality, as I've explained before. Poor quality microphone, not a very good quality loudspeaker, even though we heard the sine wave fine. One last thing, what is this noise? That is called feedback. That sound is the output from the loudspeaker going back into the microphone that is being amplified, which makes the output from the loudspeaker louder, which makes going back into the microphone that gets amplified, that makes the loudspeaker even louder, and it reaches a level of saturation that produces that sound. One of the questions on the sheets asks what happens if you remove the 10 microfarad capacitor. Now, when we looked at the original circuit for a LM386, we saw that that capacitor, which goes across pins 1 and 8, are the gain pins. So we're going to remove this 10 microfarad capacitor and let's see what happens. So I'm going to plug my loudspeaker back in. At the moment, whilst it's shifting around, we can see that the input waveform and the output waveform have a gain of 200 because we still have our original settings. And as I pull out that 10 microfarad capacitor, have a listen and have a look. So you can see that the waveform became substantially smaller, and you can hear that the loudspeaker becomes substantially quieter. I'll put it back in. And pull it back out. Now, what have we reduced that output by? Well, I'm now going to change the sensitivity of channel B, and if we read that, the output is now 1, 2, 3, 4 divisions, but each division now is worth 0.2 of a volt. So we do a quick calculation. So this is without the 10 microfarad capacitor. The input is equal to 0.04 of a volt still, but the output is now 4 divisions times 0.2 of a volt, which gives us 0.8 of a volt. So therefore out divided by in equals 8 divided by 0.04 equals, 0.8 divided by 0.04 equals a gain of 20. So now we have reduced our gain from 200 to 20. Let me remove the loudspeaker. So if we now go to the data sheet for an LM386, we can see that this was our original circuit where I took my circuit diagram from. Here is our 10 microfarad capacitor, and in this circuit here it is the same circuit but without our 10 microfarad capacitor, and it tells us that the gain is now 20. It was 200, which we calculated ours to be. Now it's 20. So that works out perfectly. If we look at this, we can get a gain of 50 by changing the capacitor, putting the capacitor back in and adding a 1.2 k ohm resistor in series with it between pins 1 and 8.